The experiment which we are going to perform is to determine reflection coefficient of a mirror and the transmission coefficient of a glass plate using a Lummer-Brodhun Photometer. So what we have to do, the aim of this experiment is we have to determine the reflection coefficient of a mirror and the transmission coefficient of a glass plate. So and the procedure is we have to use the LB photometer. So for that we need optical bench and with an additional movable perpendicular arm. So you can see this is our optical bench, and this is additional arm which is perpendicular, which is you can see this is perpendicular to this optical bench. So this is the whole setup. This is our optical bench, and that is this one is the perpendicular arm, additional arm, which is attached to this optical bench. So that is written here, optical bench with an additional movable perpendicular arm, and two sources of light. So we have two sources of light. One source of light is this, you can see, and the other source of light, let me remove it, is this, which is mounted on this optical bench. And then we need the LB photometer and mirror glass plate. Okay, so this is my LB photometer, with the help of which we have to find out the transmission coefficient of the glass plate, and we are going to use this glass plate. You can see this one side is coated, and mirror, basically this is mirror, transmission coefficient of the mirror, and we have to find out the transmission coefficient of this glass plate. The glass is mounted on this cover, which we have to use on this source like this, okay, later on. So so this is optical bench, and one is you can see this is perpendicular arm attached to this optical bench. This is our mirror, to which transmission coefficient we have to find out. This is one source. This source we will known as the movable source. We will move this source, and this other source we will fix this source to the optical bench, and this is our LB photometer. Okay, so the formula which we are going to use is for reflection coefficient is A plus B by R whole square, and for transmission coefficient is R2 by R1 whole square. So different variables which are used in the formula is R is reflection coefficient or reflection power of the mirror. Okay, so AA, which is the distance of the mirror from the LB photometer, okay, or screen. So basically the word we will use is in place of LB photometer, we will this will act as a screen. So whatever we will measure the distance, this is distance between this screen and the source, screen and the mirror, screen and the fixed source, sort of thing. So A is what is the distance of the mirror from the LB photometer screen. B is the distance of the movable source from the mirror. So this is our movable source which we will remove, and we have to measure the distance. Whatever the distance we will measure, you'll let you know during the experiment. Okay, so R is the distance of the SM from the screen when the mirror is absent. Similarly, R1 and R2 are the other things which we are going to use to find out the transmission coefficient of the glass plate. Okay, so the procedure table which we are going to use is very simple. You can see for reflection coefficient of the mirror, the first column is serial number, the second is position of SM. That is, SM means the source which is movable, M corresponds to the movable source, and then position of SC. C means the position of the screen. This means the position of the LB photometer. SF, F is for the fixed source, the source which we are going to fix. You can also see the position of the source is fixed here. And then using this, we will have to find R, which is basically say SC minus SF, the distance between the screen and the fixed source. And then we have to note down the position of the mirror where the mirror is placed, and then A is the quantity which gives you the distance between the position of the mirror and the screen, and then the last one is the separation of the movable source on the perpendicular arm, which we are going to do it right now. So the procedure is very simple, and let me tell you how to do it. Please let me put off the lights. Okay, this. Let me put off the lights. So now you can see that. So the procedure is very simple. The first thing what we have to do is we have to fix this source SF, which is fixed. So like I have fixed this source, you can see I have fixed this source, the position of this source you can see at 200. Okay, so I fixed this position of the source at 200. Okay, and then again I have fixed this LB photometer, which we will call it as a screen. The position of the screen you can see I have fixed it at 150. Okay, this is 150. Fine. And then now this is our movable source, and with the help of this movable source, what we have to do is we have to look into this eyepiece. So when you look into this eyepiece, before looking into this eyepiece, you make sure that the height of this source, which is this light is coming, matches to the opening of the LB photometer here also, and then same way you must match the height of this source to this side of the LB photometer. Okay, so now I have fixed this source. So I have fixed this source which is SF, and then the position of this LB photometer is also fixed. Now I am going to move this source which is SM, and then we'll look into the eyepiece of this LB photometer. So what you have to look for is that, let me explain you what I have to look into. It is it's like this. You will see what you will see. You will see two circles. Okay, one outer circle and the one inner circle. So what you will get, one is darker or other is darker. These two circles is going to have different brightness. So by moving the source, by moving this source, this SM movable source, what you have to adjust by looking into this eyepiece, that this two circle which I am seeing must have the same intensity of the colors. Okay, so if this is more bright, if this is because this is more bright, this is darker, so I have to move the SM. Moving SM means the source which is movable, because this fixed source and the LB photometer position is fixed, so I have to move the SM and try to make the intensity of these two areas same. So when it happens, I have to you look into this eyepiece, you will see that these two circles, and then when by moving the position, adjusting the position of the source, you have to find out the position where the intensity of the two circles becomes equivalent, almost equivalent. So at that position you have to know the position of the SM. So this is the first part of your circles. So as I said that I have fixed the position of the source, which is the source at 200. Okay, and the position of the screen means the position of the LB photometer at 150, and by moving the SM I have tried to make the intensity of the two circles equivalent, and then when it happens, then I have to note down the position of the SM. So this SM you can write it here, this SM is correct. Then you can calculate R is the SC, position of the SC minus position of SM. Now the next part what I have to do is I have to find the position of the mirror. Here what I have to do is I have to use this perpendicular arm. Okay, so what I will do is I will remove this source from here, and then I'll put this source to the perpendicular arm. So now the position will be like this. Okay, and I'll make this mirror 45 degree, till this to 45 degree, and make it closer to the screen. So now you see the position is like this. So this is my fixed source, this one is my fixed source, and then LB photometer, and then on the perpendicular axis I have fixed my SM source, which was earlier in front of this LB photometer. So this mirror I have to make it 45 degrees so that the light which is coming falls on the screen, and from here it comes to the LB photometer. So now what I have to do, because this position of this is fixed, position of SF is fixed, now what I have to do is, again I have to adjust the position of the whole this perpendicular line, and the adjustment with the adjustment of this position of the source. What I have to do is look into this eyepiece and again try to make the intensity of the two circles almost equal. So what I have to do, I have to adjust this as a position like this also, and also I have to adjust the position of the source like this, and keeping the mirror at 45 degree angle from this, and I have to find out the intensity of the two circle becomes equivalent. And when it happens, what I have to note, the position of the mirror here. Okay, the first thing, the position of the mirror, which is like this thing, and then I have to note the separation of SM. So SM is this movable source. So position, I have to find out the distance between this movable source and the mirror. So you take a scale. So what you have to do, you take a scale and try to find out the position, the distance between this movable source and this mirror. So this particular distance I have to note it down. Okay, so this is a part of the calculation. So what you get is position of the mirror and the separation between the SM and the mirror, which is put in perpendicular to each other. This is known as the B part, you see, and the A is the distance between the mirror, which we have noted down, and the position of the SC. Okay, so now I know what is A and I know what is B, and I also know what is R. So the formula was for reflection coefficient was R equal to A plus B divided by R whole square. So when using these quantities, if I calculate R, A is 28, in this case I have calculated A is 28, and then B is 18 and R is 50. So when we calculate 28, 18, 50 square, so the reflection coefficient of the mirror comes out to be around 0.84. That is 84% of the light which is falling on the mirror is being reflected. Okay, so in the same way we have to do it for three different positions of the screen, like 150, 155, 160, or you can make it like when this is, you have to fix this position, but you have, then if this is 150, I can make it like 160 or 160 or 170. You have to make the distance, you have to vary the distance for the different readings, and the other procedure will remain same for the reflection coefficient of the mirror, which you have to find out. This is the first part, to determine the reflection coefficient of a mirror. Now we'll move to the second part, in which we have to find out the transmission coefficient of the glass plate. For that, the procedure, the earlier procedure is same. What I have to do is like let me get like this. The first part of the procedure is same. As I have told you that we will fix SF, fix the screen LB photometer, and then by varying the position of SM, as we did in the case of the transmission coefficient, by moving the position of the movable source, we will try to find the position where the intensity of the two circles becomes equivalent, and then we have to note it down. The position of SM, the position of this is, and this source is fixed. So for the transmission coefficient, this position of SM, position of screen is fixed, position of SM is fixed. As earlier you can say position of fx is 200, I have kept it same. 150 by 50, and then earlier we get 96, now I'm getting 97. It hardly matters. So so the first procedure is same. By moving the source, I have to find out the position of the SM so that the brightness of the two rings becomes equal. Now in the second part, what I have to do is I'm going to use this glass plate which is mounted, or this cover, and then I will cover it on the movable source. And then by doing this, what I'm doing is I have covered this the source with the glass plate. Okay, and now again I'll move this source back and forth and try to find out the position of this SM with the glass plate, so that the intensity of the two rings, which when you see in the eyepiece, becomes equivalent, and that is, then you have to find out the position of this SM. So in the table now, this is for first part, SF is fixed, SC is fixed, and by moving the movable source, find the intensity, which is 97, and then the position of the SM movable source when I put the glass plate on it. This is SM prime. So this is, earlier it was 97, now it is 99.4. So now this SM, this value SM prime minus the screen gives you the R2, okay, and the R1 is simply distance between the SC and the SM. So if you divide R2 by R1 and square, this gives you the transmission coefficient of the glass plate. So in this case, as you see, it comes out to be almost 95%. So light which is coming through this glass plate is almost being 95% being transmitted here and is going to this LB photometer. So this is how we find the reflection coefficient of a mirror and the transmission coefficient of a glass plate. It's a very simple experiment, and what's inside the LB photometer, you can see the structure inside the LB photometer is like this. So you can see that this is SF, the two sources is SF, opening sources, and SM. So this is what I have told you. This is the two source which is towards the fixed source, and the one opening is towards the movable source. These are the two sources, and this is our eyepiece. Okay, so this you can see the two sources is there, and this is our eyepiece. So here is the screen. There's two prism is there, one prism is there, and one is a specially cut prism is there. So the procedure of inside what is happening is a different story. You can get it from anywhere, but the procedure of finding the transmission coefficient and the reflection coefficient of a mirror and the glass plate using the Lummer-Brodhun photometer is like this. Thank you.